समुद्रवसने देवी पर्वतस्तनमण्डले विष्णुपत्न्यै नमस्तुभ्यं पादस्पर्शं क्षमस्व मे. Those who dare to fly don't care to leave their footprints behind. Welcome to FVS.
Morning, everybody.
Good morning, sir.
Okay. You able to see my slide?
Yes, sir. Yes, sir.
Fine. So in today's class, we'll be taking up a third example. We considered two examples of our bigger picture of connecting loads to stresses, to strains, and then to the displacement or deformation. And through the equations, which were the equilibrium equations, the constitutive law, and the kinematics. The examples that we considered in the previous class were the axial rod, in which we showcased that the axial force is given by EA times dou U1 by dou X1, where U1 is the displacement along the length of the beam or rod. Then we went on to showcase that this is made out of two parts, the constant of proportionality. One is material dependent, the other is geometry dependent. Then we went on to a second example, which was in terms of a torsional stiffness, GJ, that we derived. And then today's example, we'll take up bending as an example, and also we'll look at, without going into the details of the derivation, plate or shell model as well, which is what we call as a two-dimensional structure, as opposed to the examples of the last class, as well as the first example today, which will be a one-dimensional example. So these, in turn, form the basic building blocks, as you know, of the aircraft structure. So we will revisit that semi-monocoque construction once again to see where these things together fall into place. And then we'll be able to understand a concept called load transfer, which is very essential, because when you're having more than one component bearing the load, there has to be some way in which the load is transferred from one to the other. Of course, we saw this in the case of the composite itself, that the fibers bear predominantly the tensile load, and then the matrix or resin, which bears predominantly the shear loads, how the load transfer takes place between them. Similarly, at a little more larger scale, length scale, what we call as the meso or the macro mechanics, we move on from not just a fiber and matrix, which we have replaced by an equivalent homogenized material, an imaginary material, which performs in a macroscopic sense in a similar way. We have now replaced that with the model which is equivalently homogenized, but now we want to look at each component, like for example the spars, the spar itself made out of two parts, the caps and the web, then the stringers, the cover skin, all of these in the case of the wing, and similarly the structures in the case of fuselage. In addition, of course, you have the transverse stiffeners, namely the ribs in the case of the wing, and the frames or bulkheads in the case of the fuselage. We will now see, because now that we have a better understanding of the one-dimensional, two-dimensional structure, how it falls into place in the overall picture of structural analysis or design, we will now take up the charge of looking at how between these the loads actually get transferred. We had considered each one of them individually and saw what kind of loads they were good at handling. Now, how the actual load comes from the outside and how it gets transferred from one component to the other is what we will try to finish in today's class. So let's get going. The example of a bending structure or a beam is predominantly the spar, because that takes the maximum amount of the bending load. So we will visit a spar in particular later on, probably in today's class. But right now we're just talking about it in a very simplified sense, as if there was just a pure bending moment which is acting on either end of this particular structure. So let me just start this. Okay. So now, once again, we need to identify these four variables for this particular problem: the load, the stresses, the strain, and the deformation. So this is the example that we are taking over here, where we are considering a beam which is subjected to the moment m2, the subscript 2 referring to the fact that the vector, which is the moment being a vector, is parallel to the x2 axis, and therefore it is indicated in that particular way. So the positive direction of m2 being along the positive x2 direction, and therefore this causing a tension on the top fibers and the compression in the bottom fibers or bottom layers. So there's no other load which is applied over here. The other end of the beam is also subjected to an equal value of the bending moment m2, so that these are self-equilibrated, and it's a statically loaded structure. But as I said, the same things can be extended quite easily to a dynamic kind of a loading situation. So this is as far as the load is concerned. It's a pure moment example that we are considering over here. Now let's go to what is the stress that is involved. So this is the load, which is m2. Next we talk about the stress. The stress that is involved in this example is the bending stress, which is sigma 11, because we have introduced the coordinate x1 parallel to the length of the beam, and therefore the stress would be predominantly a normal stress which is on this phase which is perpendicular to the x1 axis or to the b1 vector. So that is the bending stress sigma 11, which in turn is a function of x3. As you know, it's a linear function of x3, because at the neutral axis it would be 0, and it would reach positive values for this direction in which the moment is applied. It reaches positive values or tensile stresses in the top layers, and the bottom layers of this beam, it would reach maximum compressive values at the bottommost point, or at x3 is equal to minus h by 2, because as usual we are denoting the height of the beam or thickness as h, the breadth or width as b, and the length of this beam as l along the x1 direction. So that's as far as the second variable, the stress, is concerned. Let's look at the third variable, strain, the corresponding strain. Of course, there will be the other strains as well, but this is the dominant strain that is introduced because of sigma 11. It would be epsilon 11, which is the normal strain in the one direction, which again, just like the normal stress, is going to be a function of x3. Now, finally, the deformation. Very interestingly, in the case of the rod, it was very evident that if it is epsilon 11, the corresponding displacement would be u1, because epsilon 11 is defined as dou u1 by dou x1. That was what was the displacement in the case of the axial rod. But here, very interestingly, the deformation, even though the strain, look at this very interesting combination. The load is about the x2 direction, m2. The stress and the strain are in the one direction, which is sigma 11 and epsilon 11, but the deformation is along the 3 direction, which is u3. So all 3 directions are actually involved in this particular problem. 2 because of the load, 1 because of the stress and the strain, and 3 because of the deformation. So how is this u3 actually coming into affecting epsilon 11? Because we are not even considering nonlinear strains here. We are considering only linear strain displacement relationship. In other words, the kinematics is considered to be linear, what we call as geometric linearity, as opposed to material linearity, which basically means that the constitutive law is also linear. So in addition to that, we are now saying that the
strain displacement is linear. So obviously epsilon 1 is just going to be given by dou u1 by dou x1. That is a linear part of the strain displacement relationship for the 1 direction. So if that being the case, how is it that this is actually directly related to u3? What actually helps in this whole process is the assumptions that we made, which we said Euler and Bernoulli did for their engineering beam theory, what you would have looked at in your strength of materials as well. So in addition to saying that the plane section remains plane, they also made the second assumption, as we looked into in a previous class, that the section remains perpendicular to the reference line even after the bending curvature builds up. So in other words, you have this curve over here that is the reference line along the x1 direction. So whatever curvature that takes, every cross section which was originally perpendicular to the straight beam, to the curved beam also, those cross sections remain perpendicular. So in other words, at each point, whatever rotation has happened because of the curvature of the reference line, the same is the rigid body-like rotation of the cross section. Now this term, rigid body-like rotation, is very, very important because we are not considering the actual rigid body motion of this beam as a whole, but rigid body like motion of the cross section. So in other words, a cross section over here behaves like a rigid body because it was originally plane, remains plane, and as the beam reference line becomes a beam reference curve because of the curvature that builds in, this cross section at any location is going to rotate by a certain amount, and that rotation is going to be different at different locations. Now that rotation that you're going to have is of a particular cross section. So a rigid body can have 3 translations and 3 rotations, as you know. So it's actually rotating like a rigid body. But is this a rigid body motion? No, because a cross section over here rotates by a certain amount, and an adjacent cross section rotates by a slightly different amount, and so on and so forth. So for the beam as a whole, it is not a rigid body motion. It is an elastic deformation which is happening. But because we are looking at the beam as 2 separate parts, one is the reference curve, let's say the centroidal axis, that is the loci of all cross-sectional centroids. So at each cross-section, you find the centroid. If it is a prismatic beam that is the same cross-sectional size and shape throughout, then basically you are having a straight line if there's no initial curvature of the beam. So that particular reference curve is one part to the structure, which is a one-dimensional part, and then there is a two-dimensional part, which is basically the reference cross section, which has a finite area. Now this 1D plus 2D gives the real structure, which is actually a 3-dimensional structure. So when you're talking of a rigid body like motion, we are saying that it's as far as that 2D part of the structure is concerned, it behaves like a rigid body. That is, the smaller dimension behaves like a rigid body. The same thing we will say in the case of the plate or a shell, that the normal line element to a plate or shell, that normal line element behaves like a rigid body. Now here we are talking about a beam, and so the cross section behaves like a rigid body, but each cross section moves by a different amount. By movement, we mean both translations as well as rotations. In this particular example, is the rotation that actually matters. So that rotation that is actually happening over here is different at different cross sections. Hence, the beam as a 3D body, yes, it undergoes elastic deformation, so it is not a rigid body motion. That's why we introduced this hyphenated suffix like. We say rigid body like motion rather than rigid body motion. So rigid body motion would be if the beam were to move as a rigid body by itself, the entire beam. But now it's not like that. Each cross section is behaving like a rigid body, but adjacent cross sections are moving by different amounts, and therefore overall it is an elastic deformation. Now let's come back to the original question that we were trying to investigate. We are talking of a strain which is along the one direction, that is epsilon 1, whereas we are talking of a deformation which is not along the one direction. So even though epsilon 1 is dou u1 by dou x1, the deformation that we are now talking about is u3. Why is it so? Now, where this comes from is in the second of the Euler-Bernoulli approximations, where we say that the Euler-Bernoulli theory assumes that the normals remain normal to the cross-section. So in other words, the reference line, which was originally normal, continues to remain normal, even though the reference line itself has become a reference curve. It's become a curved line, but now the cross-section also has rotated along with it to move like that. So what happens when a cross-section rotates? So it's very clear that if this is, let's say, the reference line, the white pencil that I'm having over here, and now if I rotate this cross-section, so the amount of u1, that is u1, remember, is parallel to x1. So x1 is along the length of the beam. Now u1 is parallel to that. So now it's very clear to see that if there is going to be a rotation like this, that rotation is going to make points which are away from the neutral axis, which are away from this reference line, to move in the x1 direction, because the cross section is moving like a rigid body. It is rotating about the x2 direction, that is the b2 vector, same direction about which the moment is there, that is the m2. Therefore, this cross-sectional rotation that is happening is actually causing points on this reference cross-section to move parallel to the x1 direction. So the major motion is actually along the x1 direction, and how much is it will be proportional as how far from the neutral axis or the centroidal axis that particular point is. So if it is at the neutral axis itself, it has no motion because it has no strain, it has no stress, it has no motion u1. But as you go farther and farther away, whether in the positive direction or the negative direction, you see that there is a positive displacement on one side and a negative displacement on the other side, but essentially a non-zero displacement that is taking place, which should be proportional to the distance from the neutral axis in the x3 direction, that is the thickness direction for this particular problem, that is along which the dimension is h, or the height or the thickness. Now it is very clear that the maximum will be at the topmost surface, positive, and the minimum would be at the bottommost surface, which would be negative. So this is basically what we are talking about in this particular example for the direction of the bending moment that we have caused. Now how much that u1 is going to be, that constant of proportionality with the x3 is going to be the amount of rotation. But now Euler-Bernoulli's second approximation is telling us that rotation is the same as what this beam, the straight line beam that we had, has now curved by. So that curvature is what is related to u3 as dou u3 by dou x1. So in other words, that u3 is actually coming through a backdoor entry over here. Epsilon 1, yes, is actually a function only of u1, dou u1 by dou x1, but because of this particular assumption, which is a reasonable assumption for very long slender beams, u1 is equal to minus dou u3 by dou x1 times x3, and once we substitute u1 over here as minus x3, that is because it is how far it is from the neutral axis, and that constant of proportionality is the amount by which the rotation has happened, which is equal to your dou u3 by dou x1, because that is the amount by which the reference curve has rotated. And since the 90-degree between the normal and the curve and the cross section has to be maintained, if the curve has rotated by an amount minus dou u3 by dou x1, therefore the cross section also has to rotate by that amount, and that rotation multiplied by the distance, because it's small rotations and small displacements that we are talking about, at least as of now, because we're dealing with linear kinematics. So therefore, we are saying that we can substitute that minus x3 dou u3 by dou x1 into u1, and therefore your epsilon 1 now becomes minus x3 into dou u squared u3 by dou x1 squared, as you see over here. Now that is basically your first set of equations, that is the kinematics, which relates the strain to the deformation or displacement field, which in this particular case just one member of that, which is u3. Now let's look at the relationship between the stress and the strain, very similar to what we had in the case of the axial rod problem, because these are stress strain relationships are always at a particular point, and that particular point, once again we are saying we are assuming an isotropic material, because remember that constitutive law depends on the material, so we have to make certain assumptions about the material. So we are not looking at composites over here, we are looking at an isotropic material like a polymer, or it could be a metal. Now for such a material, there's no coupling with the shear and the normal. These two are decoupled from each other, but the normal themselves are coupled with each other because of the Poisson's effect, if as long as their Poisson's ratio is non-zero, and for most materials it's of the order of around 0.3 or so. So which means that there is going to be the other two normal strains, epsilon 22 and epsilon 33, which are going to result as well, but typically they are going to be smaller compared to your epsilon 11, and therefore we are not talking about it right now. But in order for a simpler expression to have for your isotropic material, in spite of epsilon 22 and epsilon 33 being there, as long as you have sigma 22 and sigma 33 equal to 0, in other words, on the edges of this beam, you're not applying any load, or you're not bringing it into contact with something else, unlike the stringers, which are actually in contact with the skin. So that is going to be kind of violated over there, that there might be a certain sigma 22 which is applied in the case of the stringer. So we are not yet going into the actual problem. We are only looking at what are the dominant kind of loading situations, and then we'll probably put them together, because we are still considering a linear material, that is linear constitutive law, linear kinematics, which means geometric linearity, and therefore the principle of superposition would be valid, and therefore we can put up all these three examples that we looked at. That is, first we looked at the axial bar, which could also be a column if the direction of the load is reversed into a compression instead of tension. The second example where we saw torsion, and now the third example that we are looking at, bending. So instead of calling it as by three separate names like bar, shaft, and beam, we are going to call it as a one-dimensional structure and use a generalized beam as the name for it, which can handle not only bending forces, which are shear forces, the bending moments, but also the torsional moments, the shear coming because of that, which we saw in the previous example. And the first example we talked about the axial force. The axial force is not a very critical thing as far as aircraft wing are concerned. Yes, in the stringers it is, but as a wing as a whole, there is no axial force, because it's a cantilever boundary condition, and there is no tip axial force or any axial force distribution along the wing. But in the case of a helicopter rotor blade, or even a propeller aircraft engine propeller, in a turboprop engine, let us say, or in any other kind of gas turbine engine, the compressor rotor blades or the turbine rotor blades, all of these are going to have large centrifugal forces, which are essentially, from a structural point of view, an axial load as well. So we are building up the possibility block by block into it in a modular structure to understand what happens to each of these individually, so that we can eventually put them all together. So in this particular example, it's important to make an assumption about the material, and also the fact that what are the actual boundary conditions, that there is no contact or force which is applied on the edges of the circumference of the beam. The only load is the moment on one end balanced by the moment in the other end, which is along the y2 direction. Now these moments are the ones which are causing this stress, and that stress is related to the strain that we have just derived using the kinematics as minus x3 dou squared u3 by dou x1 squared. Now that is in turn related to sigma 11 through a single constant of proportionality 1 by e. So what happens when sigma 2 and sigma 3 are non-zero? You just have to introduce two additional terms on the left hand side, which are going to be proportional to nu by e, and introduce those stresses sigma 22 and sigma 33, which are also going to contribute to your epsilon 11. It's not only sigma 11 which contributes to epsilon 11. So that's as far as the constitutive law is concerned. And finally, going to the last of the three sets of equations, namely the equilibrium equation. The equilibrium equation now is basically between the stress, which is what is the reaction of the material, to the load which is applied, which is M2. So in other words, we are relating the load, which is M2, to the stress, which is your sigma 11. That relationship is what is called as the equilibrium equation in this particular example. That turns out to be very similar to what you have learnt in your strength of materials. Sigma is equal to my by I. We are just making it a little more clearer in terms of the actual stress which is there, which is sigma 11, the normal stress on the one plane in the one direction, caused by a moment which is M2 parallel to the Y2 axis or X2 axis, and then multiplied by the y, or the height from the neutral plane, which in this case is the coordinate x3 according to this particular sketch that you see over here. So that being x3, we have the relationship as m2 x3 divided by the moment of inertia. This time has to be about the x2 axis, because the moment is about the x2 axis. The moment of inertia is also about the x2 axis, which is what we call as the as I22, which is going to be in turn defined as x3 squared dA. So this is the moment of inertia about the x2 axis, which is integral over the area. So it's a double integral of x3 squared dA. Now that's as far as the equilibrium equation is concerned. So now in the equilibrium equation, we can substitute for the stress sigma 11, and then we can substitute for epsilon 11 from the kinematic equation. When we do that, we get the direct relationship between the two important quantities that we are interested in, the cause being the load and the effect being the deformation. So eventually that is always going to be our important conclusion, just that we don't go to it directly. We introduce these two quantities of stress and strain in between, so that we go into it in step-by-step process. First invoke the kinematics, then the constitutive law, and then the equilibrium equation. There's no order is not important over here, because eventually we are going to substitute them all into one another to eliminate the stress and the strain, to have only the load and the deformation. The stress and the strain were only introduced to make this a step-by-step logical process. Once that is done, finally we end up with the equation that you're all very familiar with, which is that the bending moment M2 at any given cross section, which is equal in this particular problem of pure bending to the load which is applied, that is M2 at the tip load of on either end of the beam, that is equal to minus E, the negative sign of course coming from this over here, because which in turn was because of the rotation having a negative term over here. So now this is going to be minus EI22 times dou squared U3 by dou x1 squared. Now just like in the axial rod problem or the torsional problem, you don't actually need partial derivatives here, but just to keep things in general for later on to combine with situations where partial derivatives will be required, we are keeping it as dou squared U3 by dou x1 squared. We might as well in this example write it as d squared U3 by dx1 squared. So what is the difference? Obviously from the basic mathematics, you recollect that the dependent variable, in this case U3 is the dependent variable over here, depends only on one independent variable, which is your x1. So this is the dependent variable and this is the independent variable. So the dependent variable, if it depends only on one independent variable, then that derivative with respect to that independent variable is a ordinary derivative of dou squared U3 by dou x1 squared, which it should be in this particular example after all the assumptions that we have made. What was the main assumption which resulted in that? That the cross section which was originally normal remains normal. But in reality what happens is that that cross section not only has a additional rotation compared to to the reference curve what we call as the transverse shear strain, but in addition the cross section doesn't remain plane as well. That is the first assumption of the Euler-Bernoulli beam theory, or simple engineering beam theory, also gets violated, that the plane section can actually warp. People are familiar with warping happening in the case of torsion of non-circular cross sections, but it happens in actually almost all the problems. And in fact, the Poisson's effect itself is kind of a warping wherein the cross-sectional size doesn't remain the same. That is, within the cross section there is a contraction or extension depending upon whether the main load, which is the stress in the one direction, being tensile or compressive. So now that particular change in the shape and size of the cross section is in plane warping, and the plane section no longer remaining plane, that is an outward warping that is there. That is basically a three-dimensional field that results. There is an in-plane warping within the cross section, and then there is an out-of-plane warping out of the cross section. All of these will violate the Euler-Bernoulli beam theory, and in such a situation the displacement field, whether it is u3 that we are talking about here, or u1, u2, etc., are all going to be functions of x1, x2 and x3. And even when Euler-Bernoulli beam theory is applicable, but still you're dealing with a dynamic problem where u3 is a function of time, obviously you're having u3 as a function of both x1 and time, so already you're introducing two independent variables, and therefore you do need to deal with these partial derivatives over here. So that's the reason why we are retaining it there. The second important thing to see, as we did in the case of the previous two examples, is the fact that there is a material property dependence through E over here, and there is a geometric property dependence through the moment of inertia I22 over here. So it's that product which is coming into picture. So now we have been saying that the kinematics is the one which depends on the geometry, and the equilibrium equations depends on the natural laws. But why is the area in the case of the axial rod problem, the torsional constant J in the case of the shaft problem, and now the moment of inertia I22, all these three, if you look at, the source is actually coming from the equilibrium equation. The reason is that we are not applying this equilibrium equation between force and force, or between stress and stress. We are trying to involve two different kinds of quantities. One is a load, which could be a force or a moment. The other is basically a stress. On the other hand, if the load were in the form of a pressure, let us say, the stress would be directly related to that without involving much of the geometry. But here we are talking of a stress, which is actually some kind of an intensity of the load. So how much of the load is happening per unit area, and therefore that area or some geometric feature like area, like the torsional constant in the previous example, and the moment of inertia about the extrude axis, which is I22, are coming into picture through the equilibrium equation. So there is a possibility that the equilibrium equations, the way we have set it up, introduce those geometric features as well. But there is no geometry dependence as such on the equilibrium equations, because all that they are saying is that the momenta is conserved. There's a translational momentum is conserved, and the rotational momentum is conserved, because of which we end up with the Newton's laws. There's an equal and opposite reaction, so therefore we are having a balance or equilibrating between the loads and the stresses, force equilibria, moment equilibria. These are all fallouts of that. And once we go into dynamics problem, we will cheat Newton's second law by taking force is equal to mass into acceleration. We'll take the mass into acceleration to the left hand side, make it F minus ma equal to 0, and treat minus ma as a pseudo force, what we call as the D'Alembert's force or the D'Alembert's principle, and still deal with what is actually a dynamic problem as if it were a static problem. But so essentially in all of these cases, all that we are summing up is the forces and the moments. And if we were dealing only with forces in the force equilibrium equation, or only with moments in the moment equilibrium equation, there would be no geometry coming through the equilibrium equation. But now we are dealing with a load which is a moment, and a stress which is an intensity of the force, and therefore that intensity has to bring in the per unit area, and that because of that through the derivations, as you can see in your textbooks, you have encountered this particular geometric feature, which is the moment of inertia, in this case torsional constant in the case of the shaft, and the cross-sectional area in the case of the bar. So now this is as far as if only M2 is applied. But in the actual aircraft structure, which is what we are developing all this for, we know that there is not only a lift distribution which is causing a moment about the chordwise direction. So in the case of the aircraft wing, let us say we are introducing the x1 coordinate along the span of the wing and x2 coordinate along the chord of the wing, that is basically from the leading edge towards the trailing edge. So if that is the case, then your x1 vector parallel to x1, the unit vector is b1, the unit vector parallel to x2 is b2. So your b1 cross b2 is going to be downward, so you would have your x3 in the downward direction. So that is the typical convention that is used over here. So x1 along the span, x2 along the chord from the leading edge to the trailing edge. The x1 is from the root of the wing, where the wing is attached to the fuselage, to the free end. So that is the if you're considering it as a cantilever beam, from the fixed end to the free end. So that is the direction of your x1. x2 is from the leading edge to the trailing edge along the chord, and your x3 is downward. So x2, x3 are taken to be 0. In other words, the origin is taken to be the centroid of the cross section, and the centroidal axis for the entire beam as a whole becomes its reference line. But as I said, there's no hard and fast rule. You have to put it there. If you don't put it there, then your I22 is going to change. And accordingly, the stress is going to remain the same, but your moment is also going to change, because the pitching moment, for example, is going to be a constant if it's about the aerodynamic center. It's going to be 0 if it's about the center of pressure, and it's going to be some other value if it's about some other point in the cross section. So it's going to vary from point to point. So M2 by I22 is and multiplied by Y3, because the Y3 is also going to change if you're going to move the origin. So now, or X3 in this notation. So basically this entire thing, M2 x3 divided by I22, the stress at any given particular point, material point, remains the same. It should not depend upon how you choose your reference curve, reference axis, etc. We choose it according to our convenience. So for most part of the book, we would be choosing the centroidal axis, which also happens to be the neutral axis. The neutral plane is parallel to that, but it's not necessary. It could be the loci of many other quantities as well. So depending upon the convenience of a particular derivation, we choose that, but ensure that everything else is calculated with respect to that. But at any given material point, the stress value, the strain value, the displacement value, these are the three-dimensional fields, should not be dependent upon your choice of the reference frame, where you put the origin, how, in what direction you put your x1, x2, x3. All of this should not matter, because at a point the stress is a tensor, which should be independent of the choice of reference frame for its derivation. Now, so in this particular example, we took only M2, which in the case of a wing is therefore going to be coming from your lift distribution. So there is a lift distribution if this is the wing. So because of that, there is going to be a that lift is going to cause shear force at every location along the x3 direction. So the lift is in the upward direction, or actually more strictly speaking, perpendicular to the velocity, airflow velocity. So whereas the you have chosen your x3 in the downward direction, so there is basically a shear force coming because of the lift distribution integrated over, because it's a distributed load, remember. So you're going to integrate that at each cross section from the tip where the shear force is 0, bending moment is 0. So as you go inward towards the root, you're increasing your shear force, you're increasing your drag, and that drag is going to cause the shear force in the other direction as well, and therefore a moment about that direction as well. So in other words, you not only have an M2 because of the lift distribution, but a M3 because of the drag distribution. In addition, remember that there is also self-weight of the wing. This self-weight of the wing is actually not going to increase the stresses, it's actually going to decrease the stresses, because remember that the lift is almost equal to half the weight of the entire aircraft, whereas the weight of the wing is the self-weight of half the wing, which is much lesser than the overall weight of the entire aircraft, and therefore much lesser than the lift. So the weight of the self-weight of the wing is acting in an opposite direction compared to the lift distribution in a cruise kind of configuration. Of course, in some maneuvers, you have to involve the particular angles that are there. But if you consider the simplest case of the cruise flight, where there is a lift upwards, a weight acting downwards, the thrust acting in the forward direction, and the drag acting in the rearward direction. So all of these forces that are there, you typically know that L by D ratio, the lift to drag ratio, depends upon your CL by CD, and which is typically larger than 1. So the lift is going to be the dominant load, but still there is going to be a drag which is going to be contributing that as well. But if you're looking at in terms of the stress relief, you are actually having some kind of a stress relief because of the self weight of the wing, because the weight of the wing, even though it is smaller compared to the overall lift, it is actually acting in an opposite direction to the lift distribution, and therefore if the lift is trying to bend the wing upwards, the self weight of the wing is trying to bend it slightly by downward direction. So therefore it is reducing that curvature, the upward curvature of the beam, by a small amount. In addition, an ingenious design would make sure that you would have fuel in the wing. So the wing acts as a fuel tank as well, and therefore the weight of the fuel is also going to be helping you reduce the stress levels. And now, if as far as the wing shape is concerned, we as structural engineers do not have much of a control over in terms of the overall shape, the outer shape, only in terms of the interior components. But in terms of where we want to place these different components inside, not only the structural components but non-structural components like the fuel, we have some play over that. So for example, if you have the fuel, you want to have the fuel in the wing, it's actually more advantageous from a structural point of view to have the fuel closer to the free end or the wing tip, because then it is going to cause a bigger moment in the opposite direction to what the lift distribution is going to do, and therefore it is going to give a stress relief as well. So you would see that typically there are compartments as far as the fuel tank is concerned, and initially you will try to finish the fuel which is closer to the root, and then only you will start using the fuel which is closer to the wing tips, because that is the one which is going to give a much more stress relief. So you want to keep the stress levels as low as possible to the extent possible, and only finally you'll start using that particular thing. But remember that when the aircraft is on the ground, everything is topsy-turvy, unless of course it's in the process of takeoff. So it is accelerating towards takeoff. So let's say it's on the ground, static, then it's the self weight of the wing which is bending in the opposite direction. So having the fuel tank over here is going to further bring it down. But all of these nonetheless are not critical situation. The critical case is the lift distribution, and not even in cruise flight for that matter. It is going to be in certain maneuvers or certain takeoff landing conditions or climbing conditions, depending upon the actual configuration, the actual speeds involved, etc. So many factors are going to come into picture in determining those critical situations. But what is important to note is that the self weight of the wing as well as the fuel weight wherever it is placed along the wing, all of these are going to bring in stress relief as the aircraft flies, and therefore we need to take advantage of these things. Next, coming the engine. Of course, there are some aircraft for which the engine is mounted on the fuselage, but for many aircraft, especially the passenger aircraft, you would see that the engine is mounted on the wing. So now that engine is further going to give you further stress relief. Most people think that by putting the engine on the wing, you are further loading a wing which is already under so much stress. But no, it's actually bringing in a stress relief. Why? same explanation as we did for the fuel, because what are the two forces which are coming from the engine? One is the engine's self-weight. That engine self-weight is going to act downwards, whereas your lift distribution, which is a dominant load on the wing, is pulling it upwards and therefore trying to bend it upwards. The engine is going to the self-weight of the engine is going to try to bend it downwards. So now, of course, the self-weight of the engine is much smaller compared to the lift distribution values, but nonetheless, there is a small amount of stress relief that the engine can bring about. So purely from a structural point of view, you would want to put the engine as far as possible outward so that you would have a better bending moment, larger bending moment in the opposite direction to reduce the overall bending moment due to the lift. But the aerodynamist has said that you want to have tapered configuration. You want smaller and smaller cross section over there, so you may not be actually able to sustain it. So it's kind of like all design decisions, there has to be a compromise which is made, some kind of an optimization to where exactly you want to put the engine. One is the self-weight of the engine. The second aspect is the engine's thrust, which is much larger than the self-weight of the engine, because it has to equal the drag, which in turn is related to the L by D ratio, and the L in turn is related to the weight in terms of the load factor. So everything eventually boils down to the overall weight of the aircraft. So overall weight of the aircraft along with the load factor determines the lift required. Then the lift to drag ratio, that is the airfoil shape and the planform shape configuration, determines how much the drag is going to be as a function of that lift, and in turn the drag, what is the drag and what you want to balance determines what is the thrust or how much of throttle that the pilot wants to give in order to have certain amount of thrust in the different engines that he has for the aircraft. So now that thrust is therefore indirectly related to the weight. So the thrust to weight ratio plays a critical role as well. What is the maximum thrust to weight ratio, etc. But keeping that aside, what is the thrust doing now? The drag is trying to bend the wingtip backwards, right? It is trying to bend the wingtip towards the tails. But what is the thrust trying to do? Of course, the momentum is much lesser for it because it's the engines are somewhere in the midway of the span. It's not at the end of the span, but that is basically trying to, the thrust is in the forward direction. So it is trying to bend the tips towards the nose of the aircraft rather than the tail of the aircraft. So basically what is essentially happening over here is that the larger one of these two is basically your the thrust, because you're having this drag that you're having is the drag of the wing alone, whereas what we are talking about, the thrust should balance, is the drag of the entire aircraft. So essentially, even though the momentum might be smaller, you have basically the force which is going to be much larger, the thrust, compared to the drag integrated all over that. And also, of course, the drag is distributed throughout, whereas the thrust is only at a single location. Or if let's say it's a 4-engined aircraft, you have 2 of the engines on either side of the wing. So therefore, you would have at 2 different locations, you would have the thrust coming into picture. So essentially, the way the design is done, some of the things which actually seem to introduce stress are actually doing a stress relief because of the opposite directions in which they are acting. So one is the self-weight, the other is the thrust. So now therefore, we have to extend this simple problem that where we had only M2, which is coming because of the lift distribution, to introduce M3 as well because of the drag distribution. So M2 is because of the lift distribution and the weights in a cruise kind of condition, let's say. Now, as far as the M3 is concerned, the bending moment parallel to the X3 direction, that moment is going to come because of the drag and the thrust. Okay, so thrust, you can treat it as concentrated loads at particular locations where the engine is attached to the wing, and you have the drag, which is a distributed load, just like the lift distribution is having some kind of let's say an approximation like an elliptic distribution, or there's something called the Schrenk's approximation, where you take into account the actual change in the airfoil cross section and the taper that you have both in the thickness as well as the chord, and you're basically accounting for all of that apart from the elliptic distribution. So how it is going to be modified by, so various ways of estimating those things. But whatever it is, it's basically a distributed load coming because of the lift and the drag and the pitching moment as well. In addition, the pitching moment causing torsion, but the bending or shear force and the bending moment are caused by lift, drag, thrust, and the self weight of the wing, the weight of the control surface. The control surface forces, of course, would cause typically a torque. So that is just like the pitching moment. So we will not look at it right now. We are focusing on bending. So in addition to M2, before we introduce everything, see, if our point is to introduce M2, M3, which are bending moments, M1, which is about the X1 direction and therefore a torque, and in the case of let's say helicopter rotor blade, etc., F1, which is an axial force, and in the case of both helicopter rotor blade as well as aircraft wing, your F2 and F3, which are the forces which are transverse forces causing shear and therefore the shear stresses. So you have F1, F2, F3, three forces, M1, M2, M3, the three moments. But usually your F2, F3 relationship can be in the one-dimensional structure be absorbed into the M2 and M3, the bending moments, because of the kind of assumptions that Euler Bernoulli made. And even for more complex, more reliable, higher fidelity bending models, still you can live with a 4x4 matrix where you have F1, M1, M2, M3 related to U1, Phi1, Phi2, Phi3, the three rotations of the cross section, and then you build in all the warping that we talked about, both the out of plane warping as well as the in plane warping. So all that is eventually built up in a principle of superposition if it's a linear theory. But if it's a nonlinear theory, which it actually is, then you have to build it all up right from the beginning. So now that we are making all these assumptions and we're talking of geometric linearity and material linearity, we will utilize the principle of superposition and say that very similar to how M2 is related to U3, your M3 is going to be related to U2. So in other words, this converse relationship is there, and this particular relationship that we derived, one more thing I forgot to mention is that the cross section has a plane of symmetry. So the CS has a plane of symmetry, because of which the moment of inertia, of course, is non-zero, but your in this particular first part of the example, we were assuming your I23 is equal to 0. What is I23? I22 is a moment of inertia, whereas I23 is a product of inertia. So we are saying that that is equal to 0, and that is true for the case where you have a plane of symmetry in the cross section. Now if you don't have a plane of symmetry, your I23 is going to be non-zero, and first of all your M2 expression is now going to depend not only like what you did over here, which is what you see the first term over here, but you're going to now have a second term as well, this term that you see over here, that is M2 is going to depend on U2 double prime as well, because of the absence of symmetry in the cross section, and therefore I23 becoming non-zero, and therefore you bring in dependence of M2 not only on U3 double prime but on U2 double prime, that is the curvature caused not only by lift but the curvature caused by the drag as well. Similarly, we have M3, that is the bending moment which is coming because of the drag and the thrust. That is going to be related to, in a direct sense, to minus EI33 U2 double prime, very similar to what we derived over here. But in addition, because of the absence of symmetry, that is I23 being non-zero, you're going to have a term minus EI23 as well, U3 double prime as well over there. Did anybody have a question? Samanvay, yes, go ahead.
Hello sir, good afternoon. Samanvay. Okay. Sir, I'm not able to visualize I23 because, okay, in M2, U2 is due to drag. Okay. Okay. U2 double prime. Okay. Sir, I am not able to visualize what is I23 because we know I33 is when we can visualize by it is rotating about.
Yeah.
If so what is I23 exactly?
Good question. So let me explain it to you in this way. So suppose you have a symmetric cross section. What is going to happen is your M2 is going to cause only U3 double prime. But once you bring in a lack of symmetry in that cross section, or even in a symmetric cross section, if you take the axis along directions which are not along the planes of symmetry. Suppose in a rectangular cross section, I take one axis which is from the center of the rectangle towards one corner of the rectangle, and then the other axis which is perpendicular to that in the cross section. So now when you have a lack of symmetry like that, what is going to happen over there is that you are going to have a bending in one direction is not only going to cause a curvature in that direction, but is going to cause a curvature in the other direction as well. And that is driven by the fact that you have this I23, which is defined as integral of x2 x3 over the cross-sectional area A. Of course, it's a double integral, which when we say area integral, it's automatic, so I'm not showing the double integral in many situations. But this is basically what is happening over there. So, in other words, what is happening is that your lift distribution, because you know that you have an airfoil for subsonic aircraft, or for even larger speed aircraft like transonic aircraft, for the tail, you would use symmetric airfoils like, let's say, NACA 0012, where 12% is the thickness, the ratio that you are having. But this first set of zeros for the simplest kind of nomenclature you have for the airfoils basically says that there is no camber, and if there is no camber, there is a plane of symmetry which is coming over there. But once you go to some other digits over here instead of 00, you are bringing in either a positive or negative camber, and you are spoiling the symmetry that is there in the cross section. So once that symmetry is spoiled, your I23 over here is going to be non-zero. And once I23 is going to be non-zero, a lift is going to cause the lift distribution on this wing is going to cause not only bending in this way as it was doing earlier, but it's also going to cause in the drag direction there is a particular bending which is happening as well. Same way, the drag or the thrust are going to cause not only a bending in about the x3 direction, but a bending about the x2 direction as well. So this coupling that is happening is because of the lack of symmetry that is over there. Is that clear, Samanvay?
Yes, sir. So, sir, we can say that I23 is the combination of I22 and I33.
Not really.
We can correlate it. It is not really, but if we can correlate it.
See, because I22 is given by integral of x3 squared dA. I33 is going to be given by integral of x2 squared dA. And your I23 is going to be given by the area integral of x2 into x3 into dA. So dimensionally they are all the same, but it's very easy to see that x2 squared and x3 squared, which are defining your moments of inertia, are even functions, and therefore the plane if it's an anti-symmetric kind of a thing, then you would get a zero value. But you can't have an anti-symmetric geometry, so to speak. But here what we are having is a symmetric geometry, which will make odd functions when integrated over the cross section go to zero. So here you're seeing that in I23 expression, x2 is appearing as power 1, and therefore is an odd function. x3 is also appearing as power 1, which is an odd function, and therefore in either case, if there is a plane of symmetry about the x2 axis or about the x3 axis, either one of them can make this integral go to zero. So once this plane of symmetry comes in, this integral goes to zero. Therefore, the coupling between M2 and U2, and similarly between M3 and U3, vanishes. So the direct relationship is always m2 with u3 and m3 with u2, or rather their second derivatives, which is the curvature. Because the curvature is in the same direction as m2, that curvature is related to the displacement in the other direction. So in other words, your curvature about the 2 direction is related to a 3 displacement, and similarly a curvature with respect to the 3 direction is related to a displacement in the 2 direction. That is a direct relationship. But the relationship between m3 and u3 and on the one hand and m2 and u2 on the other hand is an indirect relationship, which is coming if and only if the x2 and x3 are chosen not to be parallel to any of the planes of symmetry, or the cross section does not have any planes of symmetry. So then it's impossible to choose an x2 x3 such that there will be a symmetry about them. Clear, Samanvay?
Yes, sir. Now I'm very clear.
Okay.
Understood, sir. Thank you, sir.
Welcome. So now it's clear that you have your m2 and m3 related to u2 double prime and u3 double prime through a matrix kind of a relationship. You can put a 2 by 2 matrix over here where you have m2 and m3 on one side. You have these coefficients going into that matrix, namely minus ei22, minus ei33, and similarly your minus ei23, minus ei23 into that particular matrix. But of course, once we bring in the appropriate sign conventions, the curvature that is involved is rho 2 and rho 3, that is the curvature about the 2 and 3 directions, or we can call it kappa 2 and kappa 3 curvatures about the x2 and x3 directions. Those are minus u3 double prime and minus u2 double prime, and therefore that minus gets absorbed into the curvature, and therefore the diagonal elements of that 2 by 2 matrix actually become positive, because you would have otherwise an issue with a positive definite matrix. So in other words, what we are saying is that a positive moment causes a positive curvature, and a negative moment causes a negative curvature, which is quite easy to see, easy to visualize. So now that is as far as this is concerned. The reason I'm stressing on this, even though the expression is very simple, is that already we are moving from a single scalar equation to a matrix equation. So now we were dealing only with m2 and u3 double prime in this example. We were dealing with just m1, which is the torque or the torsional moment with the dou phi1 by dou x1 or phi1 prime in the previous example. And in the first example, we were dealing with u1 prime, how it is related to f1. So now there was only 1-to-1 relationship. Now we have already brought in a 2-to-2 relationship. So in other words, we are moving from just scalar algebraic equations to a matrix kind of a representation, where you have a 2 by 2 matrix consisting of ei22, ei33, and minus ei. That minus also will get absorbed. So it would be basically your ei23 as the off diagonal elements of that 2 by 2 matrix. So now we have gone from a 1 by 1 scalar to a 2 by 2 matrix. We are going to do it further on to move from this 2 by 2 to a 4 by 4 by including the previous 2 examples into this as well. So that's going to be done shortly. But before that, let's complicate it a little more. Now, the reality is that it's not a pure bending moment which is going to be applied at the tip of the wing. It's actually a lift distribution that is going to cause this. And that lift distribution is not going to rest by only contributing to bending moments. It's going to contribute a shear force as well. Same way your self weight of the wing, the weight of the aircraft engines, as well as the in the other direction, the thrust, as well as the drag, all of these are forces actually that are distributed or concentrated. In the case of this, the weight of the engine and the thrust, it's almost a concentrated load approximately, but all of the others are distributed loads. And these distributed loads are going to cause not only a bending moment distribution, so not only you have a non-trivial bending moment diagram, but you also have a shear force diagram in both the directions that is going to come. So let's complicate that this problem a little more by introducing a shear force as well. So now we come to problem 3b, where we are having again a moment but this moment is not a pure bending moment, but a force. Let's say the same no, in the previous it was not a cantilever, it was a free beam. Now let's introduce cantilever boundary conditions and introduce a tip load V. So you see this load V at x1 equal to L. So the length of the beam over here is L. So at x1 equal to L, we are applying a tip load V. But in reality, the wing is not like this. It is actually having a distributed load, which is actually better for us, because the closer the load is to the root, it's going to cause a lesser bending moment. But as far as the shear force is concerned, this is going to be a critical case, because now the entire beam is going to have a shear load and a shear force which is equal to this particular V all the way from the tip to the root. So now for this particular problem, the load that you're going to have is going to be V. What is the stress that is going to happen? It is going to be once again on the same face, that is 1, but now you're going to have it in the 3 direction, that is in the x3 direction, that is the vertical direction, that is the thickness of the airfoil direction. So you're going to have a tau 13 which is caused over there. I'm telling it in a very loose way, because I'm only unless otherwise stated, I'm considering only the cruise condition, but otherwise I have to say that the lift is always perpendicular to the velocity direction, airflow velocity, and therefore the 3 direction that we are talking about is in that direction that we are talking about, which is along the lift direction. So here I'm using it in a very loose sense to say it's along the vertical direction, because we are considering the cruise condition. So the load is V, as we wrote over here. The stress is tau 13. The corresponding strain is your gamma 13. And the displacement that is going to take place over here is an additional rotation that is going to happen. That's gamma 13 that is there, is an additional rotation of the cross section that is actually taking place over there, and that in turn is related to both U1 and U3. So your U1 and U3 are going to contribute. But of course, in the simple example of Euler-Bernoulli beam theory, we said that they are related to each other as U1 equal to minus x3 dou U3 by dou x1. But in reality, this equation is different by this particular shear strain gamma 13 that we have now introduced. Now that gamma 13 is going to be added algebraically to your minus x3 dou u3 by dou x1 in order to actually give your u1, because there is one the reference curve is moving. In other words, the straight line has become a curve, and therefore the cross section, which was assumed to be perpendicular, is also moving along with it. So now you have a cross section which is perpendicular to that. Now you're relaxing that assumption of Euler-Bernoulli and letting the cross section to have its own rotation a little bit more. It took a joyride. It went along with this reference curve. It rotated along with the reference curve. Now over and above that, it is having one more rotation. It's like saying you're on a train and you're moving within the train. So you are having a motion because the train is moving, and then you are moving within the train. So there's an additional motion that is happening over there. Here we're talking about rotations. That's all. That's the difference over here. So now there is a rotation because of the reference curve curving up, and then there is a further rotation because of the cross section having an additional rotation of gamma 13, which has to be accounted for in this particular expression. So so in other words, your dou u3 by dou x1 was minus dou u3 by dou x1, which was the only rotation which was there of the cross section, is going to be further increased or decreased by your gamma 13 depending upon the algebraic signs that are involved over there. So now the additional thing that we have to look at is the shear force. Of course, in this case, you would have your bending moment, and that bending moment would be reaching a maximum value. If you draw a bending moment diagram, it's very easy to see that it would be 0 at x1 equal to L, and it would be a straight line which would go to, so this is the bending moment, let's say M, about the 2 directions, so it is your M2, and this is the x1 direction. So your bending moment diagram, your BMD is going to be like this, and the value at the root is going to be your tip force V that you had applied multiplied by the length of the beam, which is L. So VL is what it would be, whereas your shear force diagram would have just been a constant at the value of V. That is what it would have been. So this is your shear force diagram, and you know that they are related to each other, as the derivative of M is related to your shear force with the appropriate sign using the sign conventions, and therefore because you have a linear distribution for the bending moment, you have a constant distribution for the shear force diagram. Or other way to look at it is that you're thinking of the shear force as a integration of the bending moment diagram. So therefore it's the triangle that you have, and as you go in the triangle, the area is going to increase in a constant fashion. So that is the reason why V, which is an integral of M, is going to be a constant over there. But whatever it is, the M, the bending moment, is going to once again cause the same thing, that is your stress sigma 1,1, which is going to be related to both your M2 and M3 if the other one was there as well. Whereas your shear force V, which again can be twofold, one can be V2 and the other can be V3. The one we have shown here is actually a V3 because it is parallel to the X3 direction. Similarly, you can have a V2 which is coming. This V3 can be because of the self weight of the wing. It can be because of something which is hanging at the tip, which is causing, which is heavy and therefore causing that downward load. It could be the aircraft engine at a, somewhere mid-span location where you are having that coming into picture. Similarly, you can have, these are all V3, examples of V3 at concentrated forces at different locations along the span. Now, in addition to that, you can have your V2 as well, which is coming, let's say, from the thrust of the aircraft engine because of the drag distribution, etc. All of these. So whether it is V2 or V3, the effect is going to be a shear stress, which is going to be a transverse shear stress. In the case of V3, it is going to cause a tau 13, and in the case of V2, so this is V3, and in the case of V2, it's going to cause a stress which is going to be tau 12, right? Now, so this is these stresses are in turn going to cause your shear strain gamma 12 and eventually U2 and U1, and all of these can again be related. So without going into that derivation, the purpose of this exercise is to show what is the relative magnitudes of the maximum shear stress that you can have and the maximum bending stress that you can have, and whether it is okay to neglect one of them compared to the other for a first cut analysis. So that is what we are trying to do over here. So we are assuming a rectangular cross section, just like in the previous example, breadth of B and a height of H. That is in 3A, example 3A of the pure moment. We considered geometry like this of L into B into H. Same geometry if we consider for the shear force problem as well, that is the tip loaded cantilever problem as well. We know that the distribution in a rectangular cross section will be parabolic, like you see over here in this picture, where we have plotted tau 13 versus x3. So when we plot tau 13 versus x3 like this, we are going to get a parabolic distribution, as you see over here, with the stresses going to 0 on the top and the bottom, because the boundary conditions had to be obeyed over there, because tau 13 is on a cross section, but on the top surface of the beam and the bottom surface of the beam, that has to be equilibrated by tau 31. Which is the complementary shear stress to tau 13, and because we are not applying any load over there, in the actual problem, of course, you would have certain loads coming because of shear, etc. So there will be a small value nonetheless, but in this simplified example that we are considering over here, there should be no shear stress on the top and the bottom surface, which are free surfaces, and therefore there should be no tau 1,3 also, the complementary shear stress, and therefore tau 1,3 is equal to 0 at x3 is equal to plus h by 2 over here and minus h by 2 over here. So at these two locations, you are going to have the shear stress going to 0 because the shear stress in this particular case is plotted on the horizontal or x-axis as opposed to on the y-axis where you're plotting x3. So that is why it's like that, and it reaches a maximum at the neutral axis, and that maximum value without derivation I'm showing over here is given by 50% more than the average. What should have been the average? Because I'm applying a shear force V, the cross-sectional area is just a rectangular cross-section B into H, breadth into height. So it should have been just V by BH, but actual maximum, because it's not a uniform distribution. If it were a uniform distribution, it should have been V by BH. But because it's a parabolic distribution, the parabolic distribution can be shown to be, the shape of the parabola can be shown to be such that the maximum value occurring at the neutral axis is 50% more than this average. In other words, it is 3 by 2 times V by BH, or 3V by 2BH, as you see in this expression over here for tau max. On the other hand, for the same problem, that is the 3B problem, where you are applying a tip load on the cantilever, now if you look at what is the maximum value of the normal stress, that is going to be given by your my by I expression, and that maximum maximum bending moment multiplied by the maximum distance from the neutral axis, which is h by 2, because x3 has the range from minus h by 2 to plus h by 2. At one end it will be compression, the other end it will be tension. So we are putting h by 2 over there, and the bottom of course is a constant for the entire cross section, which is your I22. So m max and I22 are a constant for any given cross section, but m changes along the cross section, as we showed in this bending moment diagram that we drew over here, and we showed that the maximum is going to be given by V into L. So now we substitute for this m max as VL over here, and your Y max as H by 2 over here, and your rectangular cross section, you know that your I22 is going to be given by BH cube by 12. Once you substitute that and simplify it, the maximum normal stress turns out to be 6 VL by BH squared. Now if you divide the maximum normal stress, which is sigma 11 max, divided by the maximum shear stress, that is tau 13 or tau 31 max, now that ratio turns out to be, for this rectangular cross section, tip loaded cantilever, not any other problem. But for this particular example, it turns out to be 4L by H. For example, instead of a constant tip load, which is not very accurate, we introduce a little better thing, which is a uniformly distributed load, let's say Q, such that Q is equal to V divided by L. So now in such a case, this factor 4 will become 2, but nonetheless this L by H will remain. What is L by H? L is the length of the beam, H is the thickness of the beam, and obviously L by H is very large quantity. So irrespective of whether it is 4 for this tip loaded cantilever or for a uniformly loaded cantilever it becoming 2, doesn't matter. This L by H makes this ratio of sigma max to tau max very large. So even the largest shear stress is going to be of the order of 1/10, or in the worst example in this particular case, 1/40th of the maximum shear stress, because your L by H is typically going to be of the order of 10. So your L by H for most beams will be of the order of 10. Or order of magnitude is what we are talking about over here. So this is about 40. In the case of the uniformly distributed load, it is 20. In the elliptical load, it can become slightly lesser, but it's somewhere hovering around of the order of magnitude of 10, which is the order of magnitude of L by H. So unless you have very short and stubby beams, like you have in a supersonic aircraft, where you could probably have the span which is much smaller, in other words, the aspect ratio is much smaller, so there there you could probably end up with short stubby beams. You may not, in some cases you may not even be able to treat it as a beam. You might at the most be able to treat it as a two-dimensional structure, a thick shell, not as a beam, for the delta wings that you have for, let's say, fighter aircraft, etc. But for most subsonic aircraft and even transonic aircraft, your L by H is of the order of 10. That it can be for some aircraft, very low subsonic aircraft, it can be even larger than 10. So the end conclusion or inference from this is that the maximum shear stress is something that you can neglect. All that you need to really deal with is the maximum normal stress. But there are certain modes of failure which are peculiar to shear, and therefore we bring in that. And also shear is the one which is caused not only by a shear force, which is in turn caused by drag and the thrust, but it can also be caused by a torque which can be coming from the pitching moment and or the other loads, like let's say the effective the aerodynamic center being quite far away from the centroid. So the aerodynamic center for typical subsonic transonic aircraft is about quarter chord. Suppose the CG or the centroidal axis of the or the neutral axis of the wing is farther away from that can cause an additional larger moment as well. So those are all torques, and those torques are also going to cause a shear stress. Now, is that shear stress going to alter this shear stress by a lot? That remains to be seen. But nonetheless, there's a lot of time usually spent in aircraft structures courses or flight vehicle structures courses on understanding what is the effect of transverse shear and the transverse shear stress, etc. But we'll not spend too much time on that because of this particular reason, that tau max is actually much smaller compared to sigma max. So transverse shear stress is important only for short stubby beams, as I mentioned over here, where L by H is of the order of, let's say, 2 or 3. So even if it's of the order of 2 or 3, you can say for this kind of configuration, tip loaded cantilever, it still turns out to be sigma max is 10 times tau max with multiplying factor of 4. So you can see that even there it's kind of a bit of a stretch to consider this, especially for failure analysis, etc. But if you're looking at more intricate things like the mode of failure, how it is going to, let's say once there is a crack, how it is going to propagate, etc., bringing in such a certain more detailed analysis or detailed design into picture, in those situations, yes, you have to consider all the stresses because the behavior is going to be quite different in the presence of all of them. And once nonlinearities come into picture, it's not going to be a simple superposition that will be valid. So you will have to bring in all of those complications as well. So with that, I'd like to give you another homework, very similar to what I gave you for the previous case, that is the member type 2, which was for torsion, where we were trying to compare two shafts, one which is a closed shaft, which we are talking about the closed shaft as how a solid shaft is much inferior in performance with the same material thrown outwards away from the center, which is the center of the circle as well as the center of twist. If you are throwing it farther away, you see that you have an advantage. Same thing is going to happen in the case of the bending as well. In throwing the material farther away, you're going to have a better performance as far as the normal stress distribution is concerned. You can have the reduction in the stress values, you can have the reduction in the deflection, etc. So but before we go to that, we need to eliminate the effect of this. So we have shown this sigma max by tau max for a simple case of a rectangular cross section with a simple example of a tip load that I said results in a 4 L by H ratio for sigma max by tau max. And similarly, I also without deriving showcase the fact that it would be 2 L by H for the uniformly distributed load. That's very easy to see because that uniformly distributed load Q would be equal to your V by L, and it would the resultant of that would act at the center, and therefore the maximum bending moment that you would have is VL multiplied by L by 2, and therefore it will be VL squared by 2, and therefore that half factor is coming from there, and therefore this 4 will become 4 by 2, and therefore it will become 2L by H. Now I want the homework to be a little more one step further from that, so that you also get familiarized with how to derive your I22, how to derive your shear stress expressions, the maximum shear stress expression, because it is no longer going to have a parabolic distribution, which was valid only for the parabolic distribution of shear stress was valid only for a rectangular cross section. So now I'm upping the level up by going to an elliptic kind of a cross section, still not an airfoil. See, the airfoil is a much more complicated cross section, by the way. We are moving from a rectangular cross section now next level to an elliptic cross section, and instead of a tip load that we considered over here, the other example that I orally mentioned, namely the uniformly distributed transverse load, you can consider that. And now I want to change the boundary condition. Instead of going for a cantilever, which is typical of an let's say the wing, or even the stabilizers, horizontal or vertical, let's go for a simply supported beam. Is it actually important in the case of an aircraft? In fact, many people think of the fuselage as a first cut analysis to be something like a simply supported beam, with those two simple supports being the wings and the horizontal tails. So those two being the hinges on which the overhung beam is there. But instead I'm giving a little more simpler problem of a simply supported beam. In other words, the two ends are hinged, and then there is a uniformly distributed transverse load on that. But the cross section is a little more complicated, elliptic, but not as complicated as an airfoil cross section. For this case, I want you to derive tau max and sigma max, and once again show that if the ellipse is such that the elliptic cross section are having major and minor axis to be A and B, or let's say 2A and 2B, you can choose whatever. But basically, if that 2A and 2B are small compared to the length, then you are going to have a situation very similar to this. In other words, your sigma max is going to be much larger than tau max, but by what factor? How is it going to be a function of L by H, and what is the multiplying factor? Instead of 4 and 2 for the examples we talked about in the class, what is the factor going to be there? Is it going to be a function of A and B, which are the major and minor axes of the ellipse, and apart from being a function of L divided by, let's say, an average of A and B, how it is going to probably be in the case of a circular cross section, which is one extreme where A and B are equal to each other, and the other extreme where one of them, let's say A, is much larger than B. So therefore you're becoming having a very thin ellipse. You're moving very close to a typical airfoil kind of a cross section, where the thickness to the chord ratio is typically of the order of 10-12%. So you're basically dealing with that, and you might go for even smaller thicknesses for certain applications. But the eventual thing is that it's going to look like a strip very similar to what we sketched over here. That is, your H is going to be small compared to H is going to be small compared to B, and B is going to be in turn small compared to L. So this is the kind of strip-like configuration which lends itself to both beam-like model as well as a shell-like model. That is the beauty of it. A shell-like model will be a little more accurate, but a little more computationally involved. The beam-like model will be, the derivation will be very complicated, but once it is derived, just application will be very straightforward and simple, and then those derived results can be easily applied and you'll get a result, but it may not be as accurate unless, of course, you use very high fidelity mathematical, state-of-the-art mathematics mathematics and rigorous physics in order to derive those one-dimensional models. That is the dimensional reduction from 3D either directly to 1D or from 3D to 2D and then from 2D to 1D. If that is done in a fairly accurate fashion, then you would see that in such situations the loss of accuracy may not be too much. So with this, I'll come to an end of today's class. If there are any questions, I'd be happy to take them. Either on the homework or whatever we discussed in the class. If there are any questions, please feel free.
Sir, good afternoon.
Yes, Krishna Kumar.
Sir, I don't have any doubt. I have just suggestion. Sir, literally suggestion, sir.
Okay.
Sir, it would be better if you use multiple slides instead of writing in a one slide. It's looking very messy for us.
Okay, sure.
Difficult to appreciate today.
Sure. And then the idea of doing that over here, I know it's kind of cluttered, is because I want to present it in that bigger picture. So as you go, you will see that my slides will not be so cluttered. This particular example and also the previous two examples, I purposely wanted to make it because I wanted you to see all of this happening within that paradigm of load, stress, strain, and deformation, and the three connecting equations of equilibrium, constitutive, and kinematic laws. So that you can see where these things are fitting in. That is why I have it in this form. And in any case, you're going to have the YouTube video, so you can watch it over and over again and pause it and look at the notes a little more clearly. You can zoom in and look at it. So all these things are possible over here. But I did not want to lose the opportunity to present these as examples of the bigger picture, and that's why the clutter. But otherwise, even to my own students, I would say that don't have so much of clutter, because you typically don't want to have more than 20 words in a slide, and you want to keep things as less cluttered as possible, less words. People can focus on what I'm speaking. But the kind of message that I'm conveying in these three examples is very different, which is why I have done it this way, Krishna Kumar.
Okay, sir.
Okay. Anybody else? Anything?
Sir, I also have one suggestion, like
Yes, go ahead.
It's possible that we can have 5 minutes break in between.
Okay. I think you had mentioned that in the beginning. Somehow I forgot. I get carried away. So as I said earlier, please pause and let me know when you'd like to take a break. I would do that because I get so excited when I'm talking about these things that I completely forget the time moving on. So please feel free to interrupt somewhere in between where you think it's a logical motion, typically around 45 minutes, and then we could have a 5-minute break. No problem with that. Thanks for that reminder, Harshal.
Thank you, sir.
Yeah. Anybody else? Any suggestions, comments, questions, doubts?
So, one more suggestion here.
Yes, Bhārat?
So it would be better if we have feedback for our assignments. We have been getting marks for it, but it would be very much useful so that we can correct ourselves. So we don't, where we are making our mistakes, where we are losing our marks.
Okay. So that's fair enough. Are any of the teaching assistants on board? Vignesh, Renuka, and Rajesh? Yeah. So we can have after each correction is given on that weekend, you can identify one mutually convenient hour where you can have interaction with the entire student group on this same Teams platform, just the three of you along with them. And probably explain the overall solution process, the grading process, without going into too much detail. And then if they are having any doubts or questions on that, they can be clarified.
Yes, sir. For the assignment 3, the correction was actually pretty simple. Depending on the expression, the number of steps, the figures, and the references, the Rajesh, myself, and Renuka, we had a perfect grading scheme for assignment 3. So, and the assignment 3 was graded in that way.
Okay.
We have a photo of how we had
Yeah. I think we had a discussion also on one of the assignments how to go about the grading. So,
Assignment 4,
yeah,
you
right.
have a sheet of the material names and the material properties given by different students and the rankings that the students have. So we have formulated an Excel sheet.
Right.
Based on the properties and the SI units, in which proper SI units, we have actually graded the materials based on the maximum and the minimum material properties that the student has given, and in proper SI units, not in random units. So for you people who are not given proper SI units, we have reduced marks because that actually makes us to do that job for them, to do the assignment for them. So for those students, we have given 12 marks or something. But for students who have given proper material properties and proper SI units, their grades are scaled according to the material properties given by various students. For M1, M2, M3, M4, M5, and the stiffness value, the strength value, and the buckling value.
Vignesh, I suggest let's not go into too much more detail over here. I think let's make it a kind of a practice that every week in which homework is corrected and returned, you can have a 1 hour slot in the weekend, either Saturday or Sunday, where you can meet up with the students. Many times it may not need the entire 1 hour, but you can just outline for that week's assignment which was corrected and given, what was the procedure followed for the grading, and if they have any questions, doubts, that can be kind of clarified with them. So I don't need to be directly involved with that process unless if there are any issues, we can take it up later, but I am quite confident that you three are doing a great job with that. We have had a discussion on one of the homeworks already, and I'm quite satisfied with the way you're approaching this. So let's take it that way, so that you can have a more detailed discussion on the specific assignment with the students rather than with me overlooking it.
Can the students actually decide among themselves a time and give us?
Maybe you can do that over this call itself. Anybody can suggest a time, and if there are no objections, we'll fix that time.
You see, maybe they can use the Poly app.
Sure. Okay, maybe you can set up that poll, one of you, and then everybody can poll, and then choose the time which is most convenient to everybody.
Because Rajesh and me and Renuka, we are always coming with a specific way to grade the assignment.
Right.
It's actually participant independent. So
Right.
Rajesh?
Probably they had confusion regarding the assignment 4. So in assignment 4, because of relative grading, everybody got like difference in variation in marks. But it's not because of your mistake in your assignment writing and all. Everybody had done a good job in writing the assignment 4. But because of relative grading, someone has got the good material property.
Because that was the purpose. While announcing the assignment also, I had mentioned that this relative grading will be done. So the whole purpose was to identify the maximum that is possible for you to identify, and the grading was basically done on that basis. So again, Rajesh, you can explain that.
Also make sure to remove the outliers.
Right. See, we discussed this in detail earlier, so I'm okay with that methodology for the grading, Rajesh and Vignesh. So just that you can explain that in a little more detail to the students over a tutorial class rather than over this meeting. Okay?
So one thing, sir, for assignment 4, average of the class is 14.5 marks. So based on that, you can see. If you are getting 15 marks, don't assume that you got less marks. You are at average. Yes.
Sure.
That's what I wanted to say.
And relative marks and relative grading is what eventually matters. So don't worry about the absolute values. Okay then, is there anything else other than homeworks? Anybody else want to discuss something else? Okay then, fine. We'll meet on Thursday. See you. Bye-bye.
Thank you, sir. Bye,
Welcome,
sir.
Samanvay. Bye-bye.
Thank you, sir.
Welcome.
मृत्युञ्जय मन्त्राः
त्र्यम्बकं यजामहे सुगन्धिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् एते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा